Let's manually decode a UTF-8 encoded string. So here we have a little program, and we have a string here, and we have this loop that loops through it character by character and prints each character on a line. So if we run it, then you see these characters all got their own line. Within this loop here, the loop variable r is of type rune. Rune is also known as a Unicode code point. It is just a 32-bit number, and the organization known as the Unicode Consortium have agreed on which number is which letter or symbol. So all the things in this string, this was C and this A and this T and this Mao in Chinese, which means cat, all those things have a unique 32-bit number that represents them. But since they use 32, since a rune is 32 bits or 4 bytes, if you stored 4 bytes for each character, your strings will get quite large. So in order to compress that data bit, we use an encoding. And in this case, Odin uses the UTF-8 encoding. And what UTF-8 does is that, sure, the rune, which is the loop variable r here, that one is always 4 bytes. But within the string, each rune is encoded as between 1 and 4 bytes. So that for some bytes like the C and the T and the equals here, you only need a single byte, which saves you 3 whole bytes for that character in the memory. So as the loop is looping, so as this loop here is looping through this, it will decode the bytes inside it into these 4-byte runes. And that's what we print here. So what we're going to do here is we're going to look at how to manually do that decoding of the bytes. And that's good to do because then we understand how does the memory actually look, and we understand what Odin is doing automatically for us with this loop. So in order to inspect this string byte by byte, we will transmute it into a slice of bytes. So we'll do that this way: str bytes := transmute. And then we say brackets U8, and this is a slice of bytes, and we say str. Now, a string is essentially a slice of bytes, just like an array of bytes. But it has some stuff on top of it that, like some sugar on top of it, that makes it possible to automatically decode from UTF-8 into runes, so that Odin can know to do this thing. But when you transmute into this format, then we can loop over the bytes directly and look at the value of each byte. So we change this here, right, to str bytes. We can change the name of this to B and this one to B. And if we print that now, we get like all these things. So some of these letters, specifically this one and this one, use more than 1 byte each. Now, these numbers here don't really mean much to us right now, because in order to inspect the UTF-8 encoding byte by byte, we need to print them in binary so we can look at which bits each byte starts with. We can do that using this by changing the printing here a bit. So we do print ln, and then we send in a format string, and we say 8b like this. If we run it again now we get these binary. This is the binary representation of each byte. The 8 here just pads it with zeros from the left, in case, like in this case, it adds 2 zeros here, so yeah, everything lines up. So for this one, the first one here, there is a 0 at the start. A 0 means that this is a single byte character or single byte rune. So we can actually take these bits here and do like fmt.println 0b. So this is, if you want to put in an integer in binary format, you put 0b in front, then this will be interpreted as binary. If you print that, but you also cast it to a rune, remember a rune is like a 32-bit number that the printing procedures here and stuff know to represent as a character, but they're actually just a number. So you just cast this number into this rune type here. If we run this again, it says C down here. Then we can go to the next one. This one starts with 1, and then after that comes another 1 and then a 0. So this means that we count how many ones there are until the first 0. So this means that this is the start of a double byte rune. We know it's double byte because there's 2 1s. So what we do here now is we just just remove these first 3 characters. So we take this, we remove that and keep the rest. And we can put that on a line here, rune 0b. So we put that in there. But since we know we're supposed to have 2 bytes, not just 1, we will remember this for later and go to the next one. The next one starts with 10, 1, 0. The 1, 0 is it means that this byte is the continuation of a multi-byte rune. So in that case, we just throw away the initial 1, 0, and we take this and we paste it there. Right. If we now run this, we get the expected A here, which is a 2-byte encoded. It's a Unicode rune encoded as 2 bytes in UTF-8. An important thing to notice here is that Unicode, the rune or the code point in Unicode, have nothing to do really with UTF-8. UTF-8 just says how to write that Unicode into memory and how to decode it back from memory into a rune. But the rune value itself is independent of this UTF-8 encoding. So then we can go to the next byte, which is this one. This one again starts with a 0, so it's a single byte rune. So we can print that one as a rune 0b. Just run it again, you see you got a T there. And the next one is also starts with a 0. So we can do the same thing, fmt.println rune 0b. And here you also see why UTF-8, we can run this, you see you get equals there. Here we see why UTF-8 is backwards compatible with the old ASCII standard, like for English characters. Because if you think about it, a 1-byte number you can store between 0 and 255 in it, right? But if you remove, if you can't use the first bit, because that one must be 0 for this to be interpreted as a single byte character, then that range is halved. So you get 0 to 127. So when you have something starting with 0 in UTF-8, then you can use the remaining bits, which is 7 bits, which gives you a maximum value of 127. And you can use that to store something. And they decided to use the same things as the first 127 in the old ASCII standard. So that's why UTF-8 is like half backwards compatible. Like you can display the first 127 of ASCII using it, which is nice. It was nice for the transition period between when, you know, all the web pages looked a bit messed up, but sometimes looked kind of right. So we can move to the next one, which is this one. And this one starts with 111. 0. So since there's 3 ones before the first 0, it means that this is the start of a triple byte rune. So we throw away the 1s and the 0 here. So we keep this part. We throw away the 3 1s followed by the first 0, I mean. And we remember this part, we put 0b. And then since we're expecting in total 3 bytes, including the first one, we just go to the next one. It starts with 0, 1. So it's a continuation byte again. So we just throw away 0, 1 and paste the remainder onto here. A cool thing to notice here is that if you pick any byte in a UTF-8 encoded string, if you pick this one and you see 10, then you know that, oh, I picked a random byte, but I ended up in the middle of an encoded character or an encoded rune. So I can just step back, loop backwards until I find something that doesn't start with 10, and then I know I'm at the start of a character. So it is said to be self-synchronizing because of this property, because you can just look anywhere and always be able to loop backwards and figure something out from that. Let's move on to the last byte, which is this one. Again, starts with 10, and since we expected 3 bytes in total, this is our last one. We throw away the 10 and put the rest here, just paste it on here, and then we run, and you see we get our Chinese Mao character. So that's essentially UTF-8 decoding. Using this, you can inspect the memory of UTF-8 strings and reconstruct them yourself. So what you've seen here is actually just a section from my book called Understanding the Odin Programming Language. There's a section called Under the Hood, Manually Decoding UTF-8, which contains pretty much the same stuff. However, this section here, this Manually Decoding UTF-8, is just one of many sections in the book. If you're interested in the book, then you can go to odinbook.com, and there you can read a sample or you can buy it. And the book is on sale with 25% off until 9th of October 2025. Hope you enjoyed this little video. Have a nice day. Happy programming. Bye bye.